Hello everyone, this is lecture 11, example 3/71. Please make sure you read the question first before proceeding. We have a small coin that is placed on the horizontal surface for the rotating disk. If the disk start from rest and is given a constant regular acceleration, alpha, determine an expression, I updated this, determine the expression of omega in terms of alpha and r. And alpha is your angular acceleration, r is the radius, through which the disk turns before the coin slips. And we know the coefficient of static friction between the coin and disk is mu s. So this mu s will provide enough friction on the coin with a maximum omega, the angular speed, before the coin going to slip. Right? Like this is kind of natural. If I move too quick, then this correction tape would slip from my hand. But if I move slowly, this tape would move with me. So there is a friction preventing this tape, or in this case, the coin, from going away or from slipping. So we want to start with the free body diagram first. So we'll do this on this 3D diagram first. We'll follow through the G and EF method. There has to be a gravity. So we have a gravity. N stands for normal. The normal force comes from contact. We have a Fn. Is there any external force? No, no external force. And consider about friction. So friction is not on the same plane as your gravity and normal force, because gravity and normal force is on the vertical plane. However, your friction is on the horizontal plane. Right? So therefore, if we draw the force here, let me use a different color to represent it's on a different plane. Let's say there is a friction that is going this way. Okay, we have a friction. And then this friction is preventing this coin slip away. Okay, so let's say we're going to look from the top. So take another look. So if we're looking, let's say this is I, okay, looking from a top-down view, top from the on the disk, looking down. So we're looking from top. So we would have this friction going this way. And your gravity is going into the page, and your normal force is coming out from the page. And we'll just ignore them on this top view here. And then there has to be a force that is preventing this coin from moving, because if friction is the only force that exists, then on the horizontal plane, the coin will be like flying away already. So there has to be a force that is balancing with this friction. And that force is coming from the circular motion. Remember, for circular motion, there is a normal acceleration that is creating the force, mv squared over r. Okay, so we have another force here. I use a different color. So we'll just call this F. This F is unknown. Right? This force is balancing with friction, and they're equal. Therefore, we can proceed further. For circular motion, we can break the forces into different directions. And for circular motion, we can use the NT system. So on the top, looking from the top, okay, on the horizontal, it's rotating this way. So on top, if I draw this out, the rotating direction would be like this. This is the rotation direction. Okay, and this is the coin. I just simplify this as a dot, as a particle. And we can break this into the NT system. So we'll define the normal force. The normal direction is pointing towards the center, and T is tangential to the movement. So if on this diagram here, then we'll be looking at this is the N, this is the T. Okay, it's on the plane. I know it's like 3D, it's hard to see, but on top, you'll be looking at this is your NT, sorry, FT, the T direction component, and your N component is right here, Fn. And again, coming back to looking at these two forces, okay, we'll simply define going up as your y positive. We need the normal force for the friction, right? So sum of Fy equal to 0. The coin is not moving up and down. It stays on the plane. So sum of Fy is 0. And we have Fn equals to mg. And also, we know friction is equal to mu s Fn. So this is our mu s mg. This is our friction here. The friction is mu s mg, which is this guy here. And then looking at the top view using the NT system, we can find out what is normal force for the circular motion and what is a tangential force. So for the top view, we can write our sum of Fn and sum of Ft. Okay, this is your MAN, this is your MAT. Now recall from chapter 2. AN is mr omega square. I'm not using the velocity because eventually I want to express my omega in terms of the angular acceleration and r. So this is essentially also equal to mv squared over r. Because velocity is not really useful in this case, so I'm not using this one. I'm choosing the r omega square as my AN, and my AT is mr theta dot, or theta dot dot, the angular acceleration. And this can be, and we'll just replace that with alpha, because we already know the angular acceleration, theta second derivative is alpha, r alpha. Okay, these are the three equations we have. We have the friction, we have the normal direction force, and we have the tangential direction force. We want to find out the maximum force possible before slipping. So now looking back here, as our angular velocity gets bigger, gets greater, m remains the same. Let's assume r remains the same as well. So the coin will stay at this location, but greater angular velocity will create greater normal directional force. So this guy will be greater, and naturally this guy will be greater, and then this F will be greater. When your F, this capital F, is much greater than F, then they will be creating a overall non-zero resultant force and then this coin will start to slip. Either, well, should be this way, like it's being ejected out from the disc. So you have to create enough force towards the center to prevent this, prevent the coin going away. Therefore, the maximum force of this guy possible will be equal to the maximum friction this coin can obtain, which is your mu smg. Okay? Therefore, now let's write everything down. Therefore, F max before slip. This is what we want to calculate. Pythagorean theorem, F squared is Fn squared plus Ft squared. This is the total force considering the tangential direction and the normal direction in the circular motion. Copying things over, mr omega square and mr alpha square. Okay, again, we'll just do some simplification here. Combining similar terms, mr square in the bracket, omega to the power of 4 plus alpha square. So write it nicely. Our force equals to mr under the square root omega to the 4 plus alpha square. And because we want this maximum possible of the force F, so we'll make our force equals to F, and this will give us the F max. Therefore, in this case, our mr square root, this guy you just calculated, equals to mu smg. This is given by the question. We want to find out omega, okay? The omega in terms of, the question was asking, express omega in terms of alpha and r, which is here and here. Okay, we'll isolate everything. We'll isolate omega on the left-hand side and put everything on the right-hand side. I'll just keep the to the power of 4 on omega. There's no real numbers to be plugged in, so we'll just keep it simple. Mu sg on top over r square minus alpha square. This is your final answer. Done and done. Thank you for watching. I'll see you next time.